Yeah, so hello. Today I will be talking about the fire triangle. So this is a joint work with Nicolas Tabarot from the Galilee team, as I am. So I'm going to mostly be talking about CIC today. So CIC is the calculus of inductive constructions. And depending on the way you actually see that thing, you can consider it as a very powerful intuitionistic logical system that has a lot of interesting features, like, for instance, first-class notion of computation and this kind of stuff. But you can also consider it somehow as a powerful functional programming language that has very rich dependent types that allow to ensure that your programs are bug-free. Essentially, this allows to say that somehow CIC is probably the pinnacle of the Curry-Howard correspondence. And somehow, if you have trouble understanding what I mean by that, this is essentially the language that is implemented in Coq, right? So it would look like, indeed, this is a very nice system to use. Nonetheless, CIC does suffer from a huge limitation that is fundamental. So what is that thing? Imagine for a second that you've got, say, a programmer friend you want to teach Coq to. So what you do, you open your favorite IDE, and you start writing Coq code. And usually the first question that is asked by such a programmer would be, please, can you write a hello world program? And, well, this is kind of embarrassing because as I said, Coq is an intuitionistic logic or a functional programming, purely functional programming language, which somehow means that, well, you know the meme saying that code written in Haskell has no side effects because actually nobody will ever run it. And the situation is even dire in the case of Coq because obviously you don't have all the fancy imperative features that you can find in other languages, but it's worse than Haskell in the sense that you have no even asynchronous exceptions, nor even like arbitrary recursion. So you cannot, even write a non-terminating programs in Coq. And in particular, that also means no hello world because no effects. Well, this is the reason why we actually want a type theory with effects. There is another side to the coin, which is that because intuitionistic logic is in correspondence with functional programming, then the very same problem occurs for the mathematically inclined users. Typically, when the equivalent question from mathematicians is like, oh, but I would like to do classical reasoning, choice, and whatnot, and you're like, nah. Well, there are ways around, like you can have an axiom, but then it breaks the computational concept of your theory. You can try to hack things around, but it's going to behave somehow badly. So the situation is not really ideal. But the good thing is that this equivalent can be taken the other way around. Because intuitionistic logic is the same thing as pure programming, it also means that non-intuitionistic logic is essentially implemented via impure effects. Therefore, this is another motivation for having an extension of type theory with effects. Yes, this is why we want type theory. So non-termination for programmation, like non-termination exceptions, state, hello world, everything, this fancy world. But also for mathematically inclined people, you want classical logic, univalence, choice, depending on what you believe in. Great. So I hope you're on board with me on that topic. So let's have a look at what happens when you try to get effect in type theory. There is something that starts to be immediately wrong if you look in the literature. So for instance, the typical way to implement classical logic is to implement it via CPS. And there is a famous article by Barton and Ustadou saying that essentially if you try to do a CPS in dependent type theory, then you cannot really get what is called as dependent elimination. And that's a huge limitation to the thing. But there is actually worse. If you go boldly adding cold CC as the typical CPS feature via the translation to CIC, then you reach what is called as a Herbelin's paradox, which is essentially that this isn't sound. So it doesn't smell very good, if you ask me. And it turns out we've been working on doing the same thing via another way, which is called syntactic models, I'm not going to expand on that too much because I don't have time. But essentially, we're building models, an extension of type theory via some kind of program translation that must preserve type checking. And this gives us a lot of insight into what you need to preserve to be sound, right? So we do have a lot of examples like forcing, reader, exception, free algebraic effects whatsoever. We have a lot of stuff, so we've built kind of a lot of knowledge on that topic. And the harsh realization is that there's always something half broken when you create those effectual models. So something is off. Why is that we've got such a trouble? And this is not coincidence, and I'm going to explain you why at a very high level point of view. So let's consider this feature that I will call substitution. So substitution says that if you manage to prove some property A that depends on a variable x, and you have a term t of type x, then actually the property holds also for A where you substitute x by t. So this is a very straightforward property that you desire in any kind of logical system, right? This is like instantiation of formal quantification. At the same time, if you have dependent type theory, you can talk about what is called dependent elimination. So dependent elimination on Booleans, for instance, says that if you have a property P that depends on a Boolean, and you manage to prove that the property holds for true and that the property holds for false, then actually it holds for any Boolean. So this is like the on-steroid version of pattern matching, and it has all good computational content, and this is pretty expected from any dependent type theory, right? The other thing is effects. So I'm defining observable effects as existence of Booleans that are, of closed Booleans that are actually behaving in a non-standard way. That is, Booleans that are not really equivalent to a value. And those three things together sound like a desirable feature you would like to get from your type theory. And it's pretty clear that when you mix them, you get the fire triangle. So the fire triangle says that you cannot have at the same time those three properties, otherwise your type theory is inconsistent. And this is the main insight from all of our work. And the proof is quite straightforward somehow, because the idea is essentially to use those non-standard Booleans to eliminate on those things. It's really easy to do. You just prove that because there are non-standard Booleans, then they escape the dependent elimination feature because you only prove something for true or false, and it so happens that you have Booleans that are neither true nor false. And it turns out that substitutivity, the substitution property, is also critical in that argument. If you only have dependent elimination, then this is not enough to turn that into an inconsistency. So you really need the three things together. Right, so you can't complain that our notion of effect is kind of restrictive, and it actually has been reverse engineered to make the theorem hold, so I'm not very happy about that. But it is quite general enough, because most effects you can define are actually observable effects. So it's not really that cheating. Right. So now that we've got this no-go theorem, then what could we do to work around it? The major difference that is introduced by dependent type theory compared to usual simply typed or even second-order type systems is essentially the conversion rule. So that says that whenever you have a term M of type B, and you know that B is equivalent in some sense to A computationally, then actually M is also type A. And the immediate bad news means that this means that typing rules are actually embedding the runtime of your programming language. And if you consider the fact that as soon as you have effects, then suddenly the runtime becomes very sensitive to how you evaluate things. In particular, you can have different strategies that are not going to agree on your programs. If you merge those two constatations, you're in trouble. So there are two canonical solutions to the problem, either going call by name or call by value. And essentially, depending on what side you pick, then you break one or the other property. So why is that so? In call by name, by definition of call by name, you can apply substitution everywhere, so that functions are actually mathematical functions in some sense. They behave as you would expect. But the thing is now, inductive types are broken, because you can have arbitrary effects that are nested under constructors. So Boolean in Haskell, for instance, are not Booleans. A Boolean variable might loop, and this is not a Boolean. Generally, in call by value, all the inductive types are values. So you'll find, you know, that a Boolean variable is indeed a Boolean because it has been evaluated. But now the other side of the picture has been broken. The functions are not behaving properly because you need to restrict the way you substitute. So they are not real functions anymore. They are functions from value to something, not arbitrary mathematical functions. And essentially, you can picture that in dependent type theory that way, saying that substitution is a feature of call by name, whereas dependent elimination is a feature of call by value. There are three things we can act on, so there are essentially four solutions. The first one is forget about effects, and you say, right, in that case, call by name and call by value are the same, who cares, but this is CIC, so you didn't get much. The other thing is, like, you could say, right, I'm going to go call by name, and I have to restrict dependent elimination. This leads to what we call backlifting type theory. And essentially, the rule is saying that pattern matching needs to have a pattern matching type. I don't have time to describe the thing. The other thing you can do is going call by value, and then now you just forget about substitution and favor dependent elimination. And this is something not a lot of people seem to have been working on. And the last solution, obviously, is that why do you care? Actually, you could get everything at the same time and turn into an inconsistent type theory. And this is not a type theory anymore. This is actually a programming language, and this is fine. So we still have to pick a side when you want to have fx. You have to be call by name or call by value. And this is not quite true. We could have call by name and call by value, and this is essentially using what is called a call by push value that features a nice decomposition of both things. So we designed an extension of this system to the dependent case that we call the dependent call by push value with the funny D, but the name was already taken, so we had to pick a fancy name. Sorry, nothing to do with differential programming. Okay, and really, this is the main content of this article. I don't have a lot of time to discuss it, but DCBPV is actually justified with from all our models, so we have a lot of those. So it seems to be quite a general thing. The one thing we don't have yet is CPS translation for classical logic, but we hope to manage this. And essentially, the main addition is duplication of everything. That is, we get two type hierarchies like values and computation, and it is critical that computations as types are also computations. This is a critical thing. And the main addition is this generalization of lead bindings. So now we also have two lead bindings, one that is dependent and the other one that is non-dependent. And the type is actually mutually dependent. That is, the dependent lead depends on the lead. And this is validated on our models, and really see the paper for more details. So yeah, there's a lot of stuff that I didn't talk about, like good insights into the way you could restrict the system so as to preserve the computational properties of your terms. A lot of extensions of the standard call by push value encodings in the dependent case, call by name, call by value, whatever. Instances of the models, yeah, a lot of stuff. So what we did, so we think we provided a reasonable account of the impossibility of getting dependent types and fx in a naive way. You need to side with a few restrictions if you want to keep consistency. So either being pure, but that's not interesting, call by name, call by value, or completely explosive and doing programming. But even inconsistent can be used for programming indeed. And our dependent call by push value is unifying the effectful side of the picture. Probably for future work, call by value type theories have been probably a bit understudied, and would deserve a bit more attention from us. And we're still lacking a model for classical logic, but we hope that the dependent call by push value is actually correct for this model. And no implementation so far, but do we need that? I don't know. Thanks.
Thank you, Pierre-Marie. Let me start the question round with a question from Slido. So Anonymous asks, Hasn't this already been done twice by Daniel Aman and Matthijs Vakar independently?
Yes and no. So, so it depends. So the two systems are not the same. In the case of Matthijs Vakar system, is very limited. It actually falls in a fragment that is either pure or inconsistent, essentially. The rules are too strong. Most of the models require you to be somehow not observably effectful. So this is stronger. And the one from Daniel is similar in spirit, but it has limitations on the way effects can actually crawl in your terms. Like there's some kind of stratification. Here we don't have this thing. Like we don't have to separate value functions and term functions. Everything is living at the same level. So this is more powerful.
I think there's some, building on that question, there's some other ways in which this has been done as well in systems like F-star, in Idris too, to a certain extent. And I'm wondering, I think what your remarks on the earlier question I think also apply, where say in F-star there's a stratification that separates values and computation types. And I'm wondering what other kinds of properties you may be able to express in your system that couldn't be expressed in some of the other systems.
So typically these are models of CIC. So okay, let me phrase it that way. So even if you manage to get a model that is stratified, you don't get to implement full dependent types. An interesting application of this kind of constructions is to extend type theory in a safe way, so that internally you have effects, like using some kind of unsafe hatch implementation, and you prove inside your target theory that you're pure, so that you ensure you can implement new principles. And this you cannot really do in systems like F-star or Idris, because they rely on monadic presentation, so that you don't get to implement the full dependent type system. Only some restricted first order or without universe language. So
It's not really true. F-star has universes.
yeah, right. But you don't have. There is no way to. I mean, these are not really dependent types. Like the monadic thing only interprets a small fragment of the logic. It doesn't scale everywhere. Like the universes are not living in the same world as the monadic universes. You cannot extract a type from a monadic type.
So another question from Slido. I think this is more of a clarification than a question. So is delta CBPV consistent?
That depends. That depends on the model. So it's agnostic on the consistency. Depending on the actual implementation you take, then yes or no. So if you take exceptions, for instance, it's inconsistent. But the standard effect-free model is compatible with purity.
So a question from myself. So in previous related work by you and Nicolas, I think you also worked on what you call parametricity for proving that a certain term doesn't use effects. So does that somehow fit into this story? Or?
Yes, we do have like a way to recover purity in the. So I kind of lied, saying that the only pure instance was CIC is not true. You can actually use effectful type theories and rely on parametricity to cut out all the badly behaved things, so that in the end you get something like I described before, that internally use effects, but by parametricity ensure that everything is fine.
So you can, that's also in this work,
Yes.
or you've already done that, or you want to do that?
I didn't talk about it, but the presheaves can be seen as an instance of this construction where you have an underlying effectful language, and by parametricity you can really describe the naturality condition of presheaves as a parametricity property.
Okay. So we have time for one more question or two maybe.
Do you have any ideas for how to extend this proof beyond these observable effects? Because it seems like a very basic problem, right? That's just if you have more than 2 Booleans and then you have a principle that says there's only 2 Booleans and it's inconsistent.
So yeah, I agree that the definition is quite restrictive. But at the same time, we do have counterexamples to that thing that have like, by restricting such Booleans, you're fine. So I'm not claiming this is really a deep insight. This is actually somehow folklore. Like anybody coming from PLT knows this intuitively. So that's not the important thing. Rather, I think it's more like a guideline to know that there is trouble ahead.
Any final question, maybe a short one, or? Okay, so then let us thank Pierre-Marie again, and